Hello everyone. Today we're going to continue with practicing application of Laplace transform for circuit analysis. In this circuit is slightly different than what we have seen in the past. The circuit includes several capacitors, but if you notice, all of them are connected to each other, and in other words, you can use the concept of equivalency and turn all these capacitors into one equivalent capacitor. We know that when the capacitors are in parallel to each other like these two, you can add them up, the value of the capacitance, and when they're in series to each other, you use the same kind of rule that you use for resistors in parallel. In other words, 1 over inverse of equivalent is equal to 1 over inverse of each one added to each other. So if we use that, these two added to each other is a 40 microfarad capacitor, and then the two 10 and 40 in series to each other would be 8 microfarad capacitor. And doing so, I can simplify the circuit, and I'm going to start using that. But since we are going to then need to calculate V2 for this specific calculation, all we need to know is that once I calculate the voltage for the equivalent capacitor, then I have to use basically a kind of a revised voltage divider rule for capacitors in order to find out what the voltage V2 is. We're going to get there, and I'm going to explain to you what I mean by that. So I'm going to quickly redraw the circuit, and actually redraw the circuit for after the time that this switch is turned over from position A to position B. So before that, if the switch has been in the position A for a long time, we know that the capacitor, equivalent capacitor, or these capacitors basically all turn into open circuit. Since there is no current passing to the resistor at that point, the voltage on this end, assuming that we are going to obviously assume that the bottom of the circuit at this point, we start with the assumption that the bottom of the circuit in this node is our ground. That's usually what we assume, and therefore once this is 450 and there's no current, this becomes 450. In other words, for that equivalent capacitor that we discussed, the initial voltage is just 450 volts. So to redraw the circuit, we're gonna turn all of those capacitors into one capacitor with an initial voltage of 450 volts, and then since the switch is turned over, the source is no longer connected. So this is basically the circuit, equivalent circuit that I'm going to be dealing with. And now the equivalent value of the capacitor, like we said, is 10 microfarad in series with 40 microfarad, which ends up being 8 microfarad. Again, to remind you, it's 1 over C equivalent is equal to 1 over 10 microfarad plus 1 over 40 microfarad, and from that you can see that C equivalent is equal to 8 microfarad. Okay, now this is still 1.25 millihenry, and down here we have 25 ohm. So now we start labeling the circuit and continue the analysis on this equivalent circuit with the knowledge of V for this. I'm going to call this C, just call it C for this C equivalent, or C, doesn't matter. So V, the voltage of C equivalent at 0 is basically 450 volts. Okay, so with that knowledge, now we're going to move on to labeling the circuit. So I'm going to assume that's the ground. And this node immediately becomes V1, and I'm going to use that. And this node becomes V3. We are already using V2, so I'm going to use V3 for that node. And there's only one current that is passing through all the components. Same current, in other words. Okay, that's set. Now we don't have to write a KCL, and we can directly move on to writing equations for components. So equations for components. We have 3 components, therefore 3 equations. For the capacitor, down here you can see the equation for capacitor. So the current that is passing through the capacitor is equal to the capacitance, which is 8 microfarad, 8 times 10 to the minus 6 S times V1 is 0 minus the voltage on top is, we called it V3. So V1, the voltage on one end minus the voltage on the other end, which for this circuit here, it's 0 minus V3. Now minus the capacitance, which is 8, 10 to the minus 6, again, times the voltage difference, initial voltage difference, which is 450. So that becomes plus times 450 volts. So that's the equation for the capacitor. For the inductor, we're using this other equation down here. So V3, that circuit V3 minus V1 is equal to L, which is 1.25 10 to the minus 3 S times the current that is passing through the inductor. And then finally, for the resistor, that's this simple Ohm's law, which is V1 minus 0 divided by 25. Okay, so with this, we can start doing math. So we can equate these 2 equations and get an equation that relates V1 to V3. From then we put this back into this equation. We have 2 equations and 2 unknowns that relates V1 and V3, and that should do it. But to actually quickly do I'm gonna put this from these 2. I'm gonna put current here in this equation, and this becomes V3 minus V1 is equal to 1.25 10 to the minus 3 S V1 divided by 25. Now you move these around, you can quickly figure out that V1 is equal to 25 divided by 25 plus 1.25 10 to the minus 3 S V3. This is basically a voltage divider equation between V1 and V3, considering that the impedance of the resistor is 25 and impedance of the inductor is 125 10 to the minus 3 times S. So we could have actually written that equation directly knowing that, but it's a result of equating these 2 equations to each other. So now to simplify this equation so that you don't work with these really small numbers, you can actually divide both numerator and denominator by 1.25 10 to the minus 3. That's usually something that I recommend because it helps. So 25 divided by 1.25 10 to the minus 3 is actually 20,000. So that becomes 20,000 and down here you get S plus 20,000. V1, V3, sorry. That's V1. So now we have this relationship between V1 and V3. So I can replace V3 with V1 times S plus 20,000 over 20,000. And on the other end, I can replace I with V1 divided by 25, and I get an equation that only includes V1. So let's do that. V1 divided by 25. Actually, before doing that, we can also do the same thing that we did here, dividing both sides of this equation by 8 to the 10 to the minus, like in other words, multiply both sides by 1,000,000 or 10 to the 6 is going to help getting rid of these small numbers. So I'm going to do that before. So I'm going to rewrite that equation, in other words, and say 10 to the 6 I is equal to 8 minus 8 SV3 plus 8 times 450, which is actually 36 10 to the 2. It's 3,600, if I'm not mistaken. 8 times 45 is 3,600. Yes, it's 360 and then 3,600. Yes. Okay, so with that, now I'm going to replace I with this equation, which becomes 10 to the 6 V1 divided by 25 is equal to, and instead of V3 from this equation, would put an equivalent for V1, which would be minus 8 S times S plus 20,000 over 20,000 V1 plus 36 10 to the 2. So now we can move these around, move everything with that V1 to one side. So this would be V1 10 to the 6 over 25 plus 8S times S plus 20,000 over 20,000 is equal to 36 10 to the 2. So now we have to do this, so that would be V1 over 20,000. So to get 25, it's 20,000 divided by 25. That's 8 times 10 to That's 800. So that's 8 to the 8 plus 8s times s plus 20,000 is equal to 36 10 to the 2, and from this we can calculate V1 to be 36. From this you can actually simplify here, so we're going to do it later. So 36 times 10 to the 2 divided by 8 10 to the 8 plus 8s s plus 10 20,000 times 20,000. So now you simplify this, you get, interestingly enough, you get 9 times 10 to the 6 over s plus 10,000 to the power of 2. So once you have that, you can actually calculate V3 now. So from this, you can calculate V3. So V3 would be the same thing, multiplied by, so it would be 9 10 to the 6 times s plus 20,000 over 20,000 times s plus 10,000 s plus 10,000 to the power of 2, which, if you simplify that, you can get rid of this, becomes 450. So V3 is 450 times s plus 20,000 over s plus 10,000 to the power of 2. Okay. Now, I'm going to clear this region. We have already used these equations so that I can explain to you how to go from V3 to V1. So now with us knowing what the equation for V3 is, which is the voltage across the equivalent capacitor, what we need to know to calculate the voltage across the two capacitors that are in parallel is to kind of understand how to divide voltages between capacitors that are in series to each other, and that's all we need. So if you have two capacitors that are in series, C1 and C2, and you have a voltage across them, let's say the other side is ground, this is V, and you want to know how to divide the voltages between the two. There are two ways to do that. It's basically let's call that V1. V1 is C1 over C1 plus C2 times V. Now, where's that equation coming from? Well, it's really, you can calculate this from using the voltage divider and using the equivalent impedance of the capacitors in order to get this. So it would be, so the equation would be V1 is equal to 1 over C2S over 1 over C2S plus 1 over C1S times V, and that's the same equation that's you up there. You simplify that and it becomes the same equation. You get rid of S and it gives you that equation. So that said, now that I know the voltage across combined equivalent of all capacitors is this equation, I can simply find out what V1 is by multiplying them by the ratio of these two capacitors. So this one would have been the 10 micron there, and C2 is the parallel combination of the two, which is 40. So V1 in this circuit here is equal to C1, which is 10 microfarad, divided by 10 plus a parallel combination of the two is 40. So that's 10 plus 40 times V3, and now I know what V3 is. So V3, so this would be 1 over 5 V3, so that would be 90 times S plus 20,000 over S plus 10,000 to the power of 2. So now if you have to find out what the time domain equivalent of this equation is, you just have to break it down into its constitutes. So let me continue doing that. Let's get rid of this. So this would be equal to K1 over S plus 10,000 plus K2 over S plus 10,000 to the power of 2. And you calculate K1 and K2, and this becomes K1 e to the minus 10,000 t. This one becomes K2 t e to the minus 10,000 t. So the time domain equivalent, therefore the V1t is simply K1 e minus 10,000 t plus K2 t e to the minus 10,000 t. And just have to calculate K1 and K2, and I'll leave that to you. Hope this has been helpful, and goodbye for now.